All right, we're going to talk about how to determine the three-dimensional structures of molecules from looking at the Lewis structures. And the way I like to start this is with this set of simple structures that involve a central atom with only single covalent bonds. So no lone pairs, no multiple bonds to the central atom. And this is mostly about getting down or remembering the terminology. So if I have BeF2, there's two bonded fluorines and they're 180 degrees apart. This is a linear geometry. Next, I have BF3, which has three fluorines bound to a central boron atom. The angle, the FBF angle is 120 degrees here, and this is called trigonal planar. Trigonal planar because this is totally flat. Next is tetrahedral. My example here is CF4, and we have a F carbon F angle of 109.5 in a perfect tetrahedron. Trigonal bipyramidal, example here is PF5. And octahedral, example here is SF6. And because these all have bonds and no lone pairs, no multiple bonds, anything like this, all five of these have the idealized geometry. So this is a perfect trigonal bipyramid. This is a perfect octahedral. These first three geometries are encountered often when we have a central atom that has an octet or lower. The ones that are over here are expanded octet. So again, things with heavier atoms like phosphorus and sulfur. It ends up there's a few different ways to get 8 valence electrons on a central atom. So now we're going to introduce, for the tetrahedral geometry, let's start here with CH4, which has a perfect tetrahedral geometry. If we have 3 bonded hydrogens and 1 lone pair, as we do in ammonia, then we have the structure that's here, this trigonal pyramidal structure. And then finally, if we have 2 lone pairs and we have 2 bonded pairs, we get this bent structure. And the names that are given here, these are the molecular names. For tetrahedral, molecular and electronic name is the same. For this trigonal pyramidal, we are naming the atoms, not the lone pair. We're actually, one way to think about it is to put your thumb over the lone pair, ignore the lone pair of electrons, and see where that then puts your other atoms. So this is a trigonal pyramid. And then finally, if we look at just the 3 atoms of water, okay, ignore the lone pairs. We've only used them to sign the geometry. Now we look at the geometry, and the geometry is bent. Here's a, and this would be one of those slides to go back and take a look at. Here is a, as we start, these are the examples we gave where we had a central atom with just single bonds, and then as we start to have more and more lone pairs. And for the first for the first couple, it's very simple. So trigonal trigonal planar here, if we have AX3, if we have AX2E, and E stands for a lone pair, we have 2 bond pairs and 1 lone pair. What we end up with for the molecular structure here is bent. And this is pretty simple. Same deal with tetrahedral, what we just saw. We have AX4 is simple, it's tetrahedral. As one of these becomes a lone pair, now we have trigonal pyramidal, again, just looking at the atoms. And then finally, if we have 2 lone pairs and 2 bond pairs, we get bent, sometimes called angular. And we're going to skip over this one for now. Go to this one here first. So in the case of octahedral, something like SF6, if they're all bond pairs, then it's octahedral. If we have 1 lone pair and 5 bond pairs on the central atom, it's square pyramidal. If we have 2 lone pairs on the central atom and 4 bond pairs, it's square planar. These lone pairs go 180 degrees away from each other, and that leaves the bonding pairs in plane. Next, we have T-shape. And so this T shape, the first two lone pairs go 180 degrees from each other. And then all of these are equivalent, so we go in and we replace a third bond pair with a lone pair, and what we're left over with is T-shaped. And then finally, if we have four lone pairs, they go all 180, 180, and 180. And then what we're left with is the bonding pairs here are linear. All right, let's finally talk about this most complicated one. It's trigonal bipyramid. And that's because we have two sites in a trigonal bipyramid. This top X and this bottom X, we call these axial sites. And then we have three equatorial sites. And these are non-equivalent, and this only happens in trigonal bipyramid. And so when we go and we replace one bond pair with a lone pair, well, first off, we have to decide where that goes. And it ends up that these always go into the equatorial plane. So the first one goes here in the equatorial plane, and then what's left, the atoms, the AXXXX forms a seesaw. The second lone pair goes in, and now what's left for the bond pairs is a T shape, and then finally all three lone pairs go into the equatorial, and what we're left with here is linear. So most of the time, this is what we're looking for. These names that are left here, we're naming the atom positions, not the lone pair positions. We're naming the atom positions. Okay, and so this is what we said as we went through. So this guy is different than the other four because it has axial and equatorial sites. For every other geometry, all the sites are equivalent. All right, something else that can happen here. So equatorial lone pair, axial lone pair. So the SF4 molecule has 4 SF bonds and 1 lone pair on the sulfur. Would the lone pair want to occupy the red box or the blue? Well, we said as we went through, they always, for the trigonal bipyramid, occupy the equatorial side. So it ends up occupying one of the equatorial sides. And that's because the lone pairs are in fact wider than bonding pairs. So lone pairs are these big, they look like sp2 hybridized orbitals. They're these big blobs that stick out from the central atom, whereas the bonding pairs, because the electrons are shared between two atoms, are these thin, tight orbitals. And so the lone pairs require more space. It ends up there's more space to put them in the equatorial positions. And this is a rationalization for why the lone pairs go to the equatorial positions. All right, 5 electron pairs. So this is now, we're taking the trigonal bipyramid and we're going through and replacing bonding pairs with lone pairs. So this is all bonding pairs, PF5. Now when we go to SF4, it's 4 bond pairs, 1 lone pair. As promised, the lone pair goes into an equatorial site. And then what's left here, if we look just at the atoms, is a seesaw shape. Next, an additional lone pair also goes into an equatorial spot. 3 bond pairs, 2 lone pairs. So this is T-shaped. And then 2 bond pairs, 3 lone pairs. All the lone pairs always for trigonal bipyramid go into the equator, and so what's left is a linear molecule here. Okay, the equatorial positions in the trigonal plane lie in the equator of an imaginary sphere. So if you imagine this on a globe, this is just to give you some idea of where the names come from. So the equator, if you imagine this on a globe of the Earth, and then the axes, the North Pole and the South Pole. It ends up that we have, and often we don't talk about this in general chemistry, a structural effect of lone pairs. So as we said, the lone pairs are bigger than the bonding pairs. And so what happens is they squeeze the bonds down together. And lone pair repulsions are larger than lone pair bond pair repulsions. And those are larger than bond pair repulsion. So check out what happens here. So in a tetrahedron, if we have all 4 bond pairs, we get a perfect tetrahedron. If we have a 3 bond pairs and 1 lone pair, we get this trigonal pyramidal. But more than that, since this lone pair is huge, it squeezes the bond pairs closer together, so this angle shrinks. And then in water, since we have 2 big lone pairs up here, the angle gets squeezed down even more. So we go from 109.5 to 107.5 down to 104.5. The angle shrinks as we go from CH4 to NH3 to H2O. And this is just showing some real-world examples from structures. This is real data on how these things work. So this is a perfect 180 degrees. Here, these angles are 120. But when one of the sites is a lone pair, the others are bond pair, this gets squeezed down from 120 all the way down to 95. These are the ones that we talked about, slightly different angles from this different textbook. But the 109.5 gets squeezed down to 107.5 is a more common angle, and then finally down to 104.5. PCL5 here has perfect 90 degree and 120 degree angles. When one of the equatorial sites becomes a lone pair, this angle, which was 180, gets squeezed down to 173. This angle back here, which was 120, gets squeezed down to 101.6. Here in BF3, these 2 lone pairs, this angle was 90 degrees. It gets squeezed down to 86.2. But then check this out. When we have symmetric distribution of the lone pairs, since they're pushing equally on the top fluorine and the bottom fluorine, we get 180 degrees here again, because these are all pushing equally from the left and right and the front, and so it's left unaltered. Down here we have SF6. SF6, if we go over here to IF5, now we have a lone pair up here. This angle, which was 90 degrees, gets squeezed down to 81.9 degrees. And then finally, multiple bonds also have an effect. And so, for example, here with COF2, we have a CO double bond and we have a CF single bond. So in an idealized structure, we might expect for these all to be 120. For something like BF3, these would be exactly 120. But because this double bond, in fact, has more electron density, it's a thicker bond than the single bonds, what happens is this angle, the OCF angle, gets opened up, and the C and the FCF angle gets closed down. So this angle back here gets squeezed together, this angle opens up, because in fact, this CO double bond is more repulsive than the CF single bonds. Here's just another example of this. We can have this weird structure here where we have sulfur triple bond N attached. So in a perfectly tetrahedral structure, this angle would be 109.5. But the fact that this is a triple bond, which is much more repulsive than the SF single bonds, these angles all get pushed down from 109.5 to 94. Likewise, we have a structure here. If this was actually PF5, PF5 would have a 90 degree angle here, would have a 120 degree angle here. What happens is the fact, again, that this is a double bond, it's more repulsive. So this angle opens from 90 degrees to 98. This angle closes from 120 down to 112. And this angle opens from 120 up to 124. Finally, we have our clash of the titans here. We know that double bonds are more repulsive than single bonds, and we know that lone pairs are more repulsive than single bonds, but this is one of the few structures that actually lets us compare, because what's going to happen is in the idealized structure, this would be 90 degrees, we're going to have the double bond electrons push down, we're going to have the lone pair electrons push up, and so who wins? Well, slightly the lone pair wins. So we're seeing that the lone pair bond repulsion is larger than the double bond single bond repulsion. Just by a little though. So these all get pushed up just a little because this lone pair is just a tiny bit stronger than that double bond.